Hello, ladies and gentlemen. This is Miss Pashauer. We are plugging along in our 7th unit of the semester, and this one is found in the second section of Chapter 11. So, like I've said before, this unit that we're working on currently will include some stuff from Chapter 7 and some stuff from Chapter 11. What we're going to work on today are evaluating exponential functions, okay? It's not super complicated. We'll get there. We're going to talk about identifying if something actually is an exponential function, okay? If you remember what the common ratio is, what r is equal to, and how to find it, for example, 1, 3, 9, 27, and we look at what's going on here. If you can remember that from what we've done so far in Unit 7, that will be helpful in being able to say, is this something that's exponential as a function, or is it not exponential? Okay, and then the meat of our lesson today is going to be talking about graphing exponential functions. Okay, it's a little bit tricky because the graph isn't a straight line in the sense that if you graph this piece of the line, you can extend it and you can see where it would look. If you graph this piece, it's more or less having dots that you can extend. Okay, it's different when we graph exponential functions. Okay, we're going to have things that do things like this. And they, start out slow and then kind of explode up. And this particular graph, it's not a straight line, but it's a curved line, I guess, does have a part that's most important, and that's in here. Okay, these are the dots that we want to get so we can connect them and have a good idea of what that graph is going to look like. Okay, so we're going to look for where is it going to explode. Okay, that's not a technical math term, but where is your exponential function? Is it going to go like this? Is it going to go like this? Okay, what are going to be the most important pieces of that graph, and how can we make sure and pick points that will help us see those most important pieces? And that actually goes into, for here, being able to predict given the equation, the general look of a graph, the general look that a graph will take, kind of before you actually graph it. Okay, if you're looking at the equation, what's going to be important, and this is going to be reinforced in what we did in the computer lab. Okay, so let's get started. How to evaluate an exponential function. Okay, what we're going to do is basically substitute and follow PEMDAS. Okay, so this is a real life example. F of x is equal to 2 times 3 to the x power, and it models an insect population after x days. What will the population be on the 5th day? And so therefore, if x stands for the number of days, and we're talking about 5 days, what population will the insects, how many insects will be in this insect population? So basically, substitute, follow PEMDAS. Okay, f of 5 is the way of writing this, so I know what I'm putting in here, is 3 to the 5th power. Okay, the only tricky thing is make sure you do exponents before you do multiplication. That is how PEMDAS works. You're going to want to have a calculator handy as you go through these problems today. So the first thing I'm going to do is start with 3 to the 5th power. 3 to the 5th power is fairly big, and it is 243. Okay, I still have my 2 times here. So basically now is when I can multiply times 2, and my insect population will be at 486 insects. Pretty gross. That's a lot of insects. Okay, it grows exponentially, this particular example, because as you have more of them, more of your insects are having more babies and more babies and more babies and more babies. Okay, it's not a linear growth here. Okay, before we might have had a straight line of how things grow. It's different now, okay? We'll get into graphing, but we're going to see a very different shape of the graph when we talk about exponential functions. I would like you guys to do number 2, so go ahead and hit pause after I finish reading the question. The function f of x, 1,500 times in parentheses 0.995 to the x power, models where x is the time in years, and it models, a prairie dog population. How many prairie dogs will there be in 8 years? So go ahead and try that one. Grab your calculators and hit pause right now. Okay, ladies and gentlemen, hopefully you're back. The answer here is about approximately, okay, your calculator is going to give you kind of probably a long decimal here. We round it to 1,441 prairie dogs. We can expect that these prairie dogs are actually going down in their population. Okay, too many predators are eating the prairie dogs, or there's not enough homes for the prairie dogs to live, whatever it might be. We saw, interestingly, that their population decreases. Okay, so that's our first objective of the day, just evaluating exponential functions. Pretty quick and easy. Let's keep going. Next, we're going to talk about, can you take a look at some ordered pairs or take a look at a table and tell me if it's exponential. Okay, this orange line here is important. Functions in which the output values grow as a constant multiplication from one term to the next are called exponential functions. Okay, we've been dealing with these since the beginning of when we jumped into chapter 11. We're basically looking for what is this constant value. Okay, this piece here is very important. Okay, this here. What pattern are we seeing in the output values? Okay, the output values, one way of that, usually those are the y's. Okay, in this case, in this real life example, it's the population, because the population depends on time. So I think we're again talking about some bugs. Okay, you can see here we're talking about some bugs. The graph of what's going on with these bugs, I'll erase my fireworks here, is over here. Okay, we can see if we wanted to connect these dots, we would have kind of this curved line that starts out gradually growing and has an explosion where it gets almost vertical. It's never going to get all the way vertical, but it's growing. And like I said, when we do these graphs, this piece here is really the most important points to graph of that line. If you don't happen to graph those points, you have a hard time seeing what that function is going to look like when it graphs. So let's go back to the table here. We have an insect population that on day 1 is 2. Those insects have some babies, and now we have 6 insects after day 1. After 2 days, we have 18, and after 3 days, we have 54. So again, we're looking for a pattern. Do we see a constant multiplication here? The numbers are small. It's nice to say, oh, well, that multiplies by 3. As long as it continues to multiply by 3, you're going to have an exponential function. Okay, it will be exponential if you can find a common value that is multiplied in each case by every y term, output value, in this case population. Okay, if you get a multiplication of 3 of 3 of 3 in the output values as this increases by 1. Okay, if your x values, in this case it's time, don't increase by 1, you are going to see jumps here in the y's. Okay, so make sure your x values are going up by 1 unit, whatever that is, and then you can look for a constant change here. A multiplication, remember, if it looks like it's dividing, we talk about that as a multiplication of a fraction. So this is important, this know-it note. I kind of like, they tell you, hey, write it down. An exponential function has the form f of x is equal to a times b to the x power, where a is not 0, b is not 1, and b is greater than 0. Okay, lots of little characteristics there. Why don't you guys hit pause and write down this formula that you see in the nice tan box. Okay, now we're going to start some actual example problems. These are 2 different set of ordered pairs. Now, when you do your homework, when we do some example problems, and also probably on a test or quiz, they're just going to give you the coordinates as ordered pairs. You know, x comma y, x comma y, x comma y. For me, it's a little harder to see a pattern when I just am looking at coordinates. So for me, I almost always actually take my ordered pairs and write them into a table. So it's much easier to see what's going on here when you put it into a table. Obviously do what you prefer, but I think you'll get the right answer more often if you organize your information into a table. So the first thing to make sure that we have is that x is growing by 1. If x is growing by 1, in this case -1, 0, 1, and 2, we can actually just take a quick look at the y values and see if we see any sort of pattern happening as a multiplication. So I have 1.5 goes to 3, 3 goes to 6, and 6 goes to 12. Not too hard to see that we're multiplying by 2 each time. So this is an exponential function. Okay? As the x values increase by a constant amount, the y values are multiplied by a constant amount as well. Okay? Let's do another example. Let's go to B. Okay, this is just a yes or no question. Yes, it's good to know that, hey, in this case, R is 2. You have to look for it to know if to answer yes or no, but it's not necessarily part of what you're going to answer. Okay, we're just looking for a yes or no question. Now, my next box, okay, the first thing to notice is x going up by 1. Oh, but this case, x is going up by 2. It's still a constant amount, so it's okay. Okay, if x were going plus 2, plus 1, plus 2, plus 1, that's not going to work. Okay, as long as x is increasing by a constant amount, we can look for, hey, is y increasing by a constant amount? And here we see y values going negative 9, 9, 27, and 45. Okay, what is happening? I'm multiplying by negative 1, I'm multiplying by 3, and I'm multiplying by some decimal here, 5/3. This is not going to be an exponential function. Okay, it's not going to be an exponential function. Why? Because as the x values increase by a constant amount, the y values are not multiplied by some constant amount. Okay? So if you want to pause and write any of that down, that's a good idea. Otherwise, I'm ready to move on. So if you want to pause now. Otherwise, we're moving along. Okay, next we're going to talk about graphing. Okay, like I said, graphing is going to be the meat of this lesson. And to graph exponential functions, as we know of now, with paper, pencil, and a piece of graph paper, we're basically going to be choosing points. Okay, we're going to pick x values, plug them into x here, see what y is, and we're going to come up with a bunch of dots. Okay, we're going to graph our lines by simply graphing several points that are on the line and connecting the dots. Okay, so choose several values of x, plot the points. Once you get them, generate ordered pairs, that's important. Choose several values of x, plug them into your formula, just like we did in the first slide of this lesson, and find out what y has to be. Okay, plot the points and connect them with a smooth curve. This table right here is almost something that you just kind of have to commit to memory. Okay, our formula for an exponential function is this. A is any coefficient that might be in front. B is another constant value. And then x is some sort of x. X is going to be actually part of, you're not going to have a number for x. You're going to have a value of x as an exponent. And so, like I was saying, this table, again, just kind of something you might want to commit to memory. If we have exponential functions, they are going to have this explosion point. And that explosion point is going to happen in one of your 4 quadrants. Okay, in this case, I'm just going to kind of trace these here if you follow me along in the box. When a is greater than 0. Okay, when this value here is a positive number, more or less. When a is greater than 0, it's going to start out small over here in the second quadrant, have an explosion here, kind of in between the first and the second, and then get really big up here in the first quadrant. Okay, if a is less than 0, if a is negative, you're going to start out slow, more or less the same on the left side. In the third quadrant, though, here, where as you hit the y-axis, you're going to have these explosion point going downwards, and then you're going to have that continue in not vertical, but in almost vertical fashion. Okay? And this is also if b, your b value here, is greater than 1. Okay? So if b is 2, 3, 4, 5, anything like that, anything that's more or less, bigger than 1, you're going to have this explosion happen here on what I would call kind of the right side of the graph. Okay? Let's talk about the other option. Oopsie. If b is in between 1 and 0. Okay, so if your b value is a decimal or a fraction that's greater than 0 but less than 1, you're going to have this explosion happen on the left side of your graph. The left side of your graph. And more or less the same thing happens with the A values. You don't have to memorize that too much. It's almost logical. If A is greater than 0, you're going to explode upwards. Okay? If A is less than 0, a negative number, you're going to explode downwards. Okay? So what I would do right now is pause and copy down this chart. Okay, let's try some examples. Let's try some problems. This is our last slide of the day. I'm sorry. We have this one and one more. This one here actually talks about how to identify if something is an exponential function. I'll do one with you, and then I'll ask you to do the second one. If, like I was saying before, if I'm given a list of points, it's kind of hard for me to see the relationship of those, so I put them in a table immediately. Okay, I take this point here, and I plug it here into my table. This point goes here, and I just plug it along. How do I tell if this is an exponential function? Well, I make sure that this is going up at a constant amount, and then I look at, hey, what is going on? What is going on the right side? What's happening here, and here, and here? Well, my y's seem to be multiplying by 0. Multiplying, how do you go from 0 to 1? You add 1? That's weird. And here you multiply by 4. This is definitely not an exponential function. Okay, this is not an exponential function because as the x values change by a constant amount, the y values are not being multiplied by a constant amount. Why don't you guys try the second one? Why don't you guys hit pause, put these into a table, see if you find anything interesting and come back. Okay, I assume you're back. This is what I have for an answer. I plugged my values into a table. The x values are going up by a constant amount, in this case 1. So what is going on here is the big question. I am multiplying by a half. I am multiplying by a half. I am multiplying by 1/2. Okay, so this is yes. Hopefully you got yes. Okay, that was a topic we talked about a little bit earlier in the slides. So let's go back to graphing. Let's go back to graphing. What's tricky about graphing is we have to create points. We have to pick x values. Okay, so when we graph, we're going to pick x values. This was in our notes earlier. Hopefully you wrote it down. We are going to evaluate, and we're going to plot our points. It's important we pick the right x values. Okay? So, in example A, the first one, what I'm going to first do is figure out what is A and what is B, because that's going to help me take a prediction at what kind of graph I might have in store for me here. So let's see. Our formula here, y equals AB to the x power. So A is, hopefully everyone's saying it at home, A is 3 and B is 1/2. I like to write that down. It helps me to see what kind of graph I'm going to be having show up. So if A is positive, I must have one of these blue ones in my chart here, the blue ones in the chart, but B is a half. B is a half. So now I'm definitely looking at this right side here. So I should expect this type of graph here. I want to make sure to pick values like these negative ones here, maybe a few positives, but also some negatives. So in this example, I chose making sure to pick x of -1, x of 0, 1, and 2. Okay, do I get, when I plot those points, something that kind of explodes in the way that I expect it to? I most definitely do. Okay, so this is the procedure for graphing as we know it with exponential functions. I would start by looking at the table, the chart up here at the top that I'm erasing these arrows at. Take a look at this nice tan chart so you can kind of predict what graph you're going to get. Pick points that are important on that graph. Choose your x values, plug them in. Okay, you might be asking, how did I get 3 and 6 and 1.5 and 0.75? Well, I took -1 and I put it here. I took 0 and I put it here. I took 1 and I put it here. Okay, we're evaluating 3 different times. To evaluate means to substitute and follow PEMDAS. I want you guys to try 1, and then we're done with our notes. Okay, I'm going to try and leave that chart up there for you. But I want you to hit pause now, and I want you to do B. Okay? Before you hit play and have me come back and reveal the answer, ask yourself, is it what I expect it to look like up here in the chart? Okay? Go ahead now. All right, I assume you're back. Let's make sure your answer matches mine. I'm going to leave this there for a second. Sorry, going up and down. What is A and what is B? Okay, what is A and what is B? And maybe I need a little bit higher. Okay, y equals AB to the x power. So in this case, A is -2. Hopefully you wrote that. B is 0.4, another one that's between 0 and 1. But now my A value is negative. So if A is negative, I expect something that's going to kind of go down. It makes sense if you got something negative. And so hopefully I'm thinking that we're looking for that type of graph there in red. Okay, choose several points. If you're looking for a minimum, I would say 4. And what do I get? And again, hopefully you used your calculator there. Hopefully your graph looks like mine. Okay? So this is the graph of that exponential function. Y equals -2 times 4/10 to the x power. Okay? If you have any questions at any point, please write them down right there in your notebook. Follow along through the videos. If you weren't sure why something happened the way it did, go back and rewatch. But basically here we're graphing just by picking points, plugging those values in. I took my -2 and I plugged it in here for x. -1 and I plugged it for x. You don't have to pick the exact same points that I did. You don't have to pick these exact same points. But if you don't pick good points, maybe in this case my graph looks like this. And if you just happen to pick this point and this point and this point and this point, you might think the graph does that. But it doesn't. Okay, it's important to pick the important points. Okay, so hopefully you're feeling confident about these objectives. Can you evaluate exponential functions? PEMDAS. Substitute and do PEMDAS. Can you identify exponential functions? Okay, can you look for that R value if it has it or if it doesn't have it? And can you graph? Okay, please, think about this formula here and how your graph is going to change depending on what is A and what is B. Okay, have a great evening, ladies and gentlemen. We are all set. I will see you tomorrow.